Hello, and welcome to another edition of the Forecast Contest webinar series. My name is David Margolin, and I'm today's host, and I'm very excited to introduce today's guest speaker, Professor Brian Tang from the University at Albany. Professor Tang's research focuses on tropical cyclones, hurricanes, and severe thunderstorm. In today's webinar, Professor Tang will provide an overview of tropical cyclones, and in particular, the tools and guidance that are available to forecasters, such as those at the NHC, for making tropical forecasts. And the timing of the webinar, of course, is perfect because we're just a few days away from the start of the hurricane season. And as I was mentioning to Professor Tang a minute ago, we're already seeing the GFS and some of the models show some potential hurricanes, at least far out there. In terms of the format of today's talk, we'll ask that all of our audience members remain on mute, but we encourage you to submit questions via Zoom chat, and we'll try to get to many of those at the end of the webinar. Without further ado, over to you, Professor Tang.
Thanks, Dave. So as you mentioned, we're on the doorstep of the 2022 Atlantic hurricane season, which, according to seasonal forecasts, appears like it's going to be another active one. So as we gear up for yet another hurricane season, I want to share with you some of the forecasting tools that I typically use whenever there's an active tropical cyclone or a disturbance out there that has the potential to form. And particularly focusing on my own website, which I know has certainly gained in popularity over the years. So let's get right into it. So I just want to begin with just some fundamentals, and these are the forecast variables that we're typically concerned about. Certainly there's many aspects of tropical cyclones that we're interested in, but there's a few forecast variables that are common. First thing is when we have a tropical disturbance, just a cluster of thunderstorms like an easterly wave coming off Africa. Obvious question is, will it form into a tropical cyclone? So formation is one forecast variable we're interested in. Once a tropical cyclone forms, we're interested in where it's going, its track. Part of that is the position, but also how fast it will move is also an important variable. And I like to relate it to particular hazards. Why do we forecast these variables? Well, track obviously affects which communities will experience hazards. The hazards being damaging winds, storm surge, heavy freshwater, heavy rainfall causing freshwater flooding, and onset and duration of hazards. For preparation, usually the onset of tropical storm force winds is the cutoff between when emergency managers want people to prepare versus finish evacuating, starting to shelter in place. And also the duration of hazards is really important. The duration of hurricane force winds related to damage, the duration of inundating rains, right, affecting flooding. Those are all affected by the track and how fast a tropical cyclone will move. Next obvious one is intensity. How strong will a tropical cyclone be? Usually intensity is, at least from a impacts perspective, is measured through the maximum sustained near surface wind speed. The wind speed, particularly the gusts, are related to damage and losses, something the insurance industry and risk industry is very much attuned to, is wanting to know what the maximum wind gust is going to be. And also things like storm surge. Storm surge non-linearly increases with wind speed, and so does damage and losses, as the data shows. A particularly underappreciated aspect of tropical cyclones is size. How large will the tropical cyclone wind field be? And this can greatly influence hazards, things like, again, the duration of hazards. Storm surge is directly related to size, and amount of rainfall oftentimes is related to the size of the storm itself. For this particular talk, I'm going to focus on the first three, especially the track and intensity, since those are kind of the common variables that people are interested in. Okay, so let me launch right into specific forecast tools that I like to use when forecasting tropical cyclones. By all means, this is not the only set of forecast tools that are out there. I'm certainly biased in what I'm familiar with. So, if this were the sound and music, these are a few of my favorite things. Okay, so formation, straight off the bat, straight to the source, the National Hurricane Center, the tropical weather outlooks, getting the expert perspective of what they're thinking. But in terms of specialty guidance that's out there, I oftentimes use the products from Sierra, and they have an operational product. But they also recently, Alan Brammer presented this at the recent AMS conference on hurricanes and tropical meteorology. They're starting to incorporate ensemble data in some of the ensemble tools that they use. So this is just a sample figure from this ensemble product. So you can see these cones of uncertainty where the tropical disturbance may develop. The tropical disturbance usually abbreviated in Atlantic by AL, and then and then the number in the 90s. That's how you know it's a disturbance or an invest. And then the percentages over various days, short-term formation probability, and then the long-term formation probability given by the numbers here. So a really great product that I'm going to certainly be looking at over the course of the season. So my go-tos for almost everything, formation, track, intensity, other variables, the SIMS page, this has been around for a while, operated from the University of Wisconsin, the SIMS group out there. And this is really good for looks at the environment, things like shear, things like the SST, and a lot of satellite observations that they incorporate into their products. It's a really valuable tool to get kind of a broad scale, and also looks at the tropical cyclone itself. Tropical Tidbits, another very popular website. If you're familiar with forecast model data and tropical cyclones, you probably heard about Tropical Tidbits. Really valuable for visualizing reconnaissance observations in near real time. Model, it's great for model output and also satellite imagery. So it's, in terms of a one-stop shop for tropical cyclones, it's pretty close to that. Another really great website is Weather Nerds. Things like ensemble data has a really great visualization for ECMWF ensemble data, spaghetti plots, and also intensity overlaid on top of that. Weather Nerds also has a customization feature where you can overlay fields of interest that you want to plot, zoom into various domains. So it's a really great website for creating custom plots. Both Tropical Tidbits and Weather Nerds also have the options for cross sections and point soundings, which I find very valuable as well. And then going back to Sierra, they have a great resource, satellite imagery and model diagnostics now, but their model diagnostics plot is one of the things I go to time and time again for a quick look at the forecast data and some of the verification, short-term verification. For track and intensity guidance specifically, there is a tropical cyclone guidance project from the Research Applications Lab at UCAR. Clark Evans has his hurricane forecast model output, which has a great interface and also some verification statistics. There's the Hurricane Forecast Improvement Project, their tropical cyclone storm tracks. So if you're interested, particularly outside of Atlantic, this site, you can plot tracks from a variety of models for both the Atlantic, but also in other basins. So this is a great resource for that. And then perhaps a little bit less known, but really great stuff, is the AOML Hurricane Model Viewer. This is their in-house model viewer. You can literally spend the entire day looking at all the variables that they have. Particularly of interest is the Hurricane Analysis and Forecast System, the HAFS model, which is the next generation hurricane model. That's the FE3 based hurricane model that they have a variety of diagnostics for. It's a really great resource, and it's one that, particularly if you want to really dig into the environment around tropical cyclones and the tropical cyclone structure itself, it's a really great tool. Okay, but I'm going to focus on my thing because it's me, right? So I'm going to focus on my tropical cyclone guidance page. And since there's really nothing going on out there, what I've done is I've rerun the graphics for Hurricane Grace from last season. And I'm going to just step through what I offer on my webpage so that you get an idea of what the various products are. So first of all, similar to the other websites that I mentioned previously, I have just the traditional plots of deterministic track and intensity guidance. So here's on the figure here, it just shows tracks from various forecast models, both global models and regional hurricane models. Each of these colored lines represents a different model. So this purple line is the HWRF model. This blue line is the ECMWF, and so on and so on. And the numbers just show the forecast hour ahead of the time in which this plot was generated, or the initialization time of the models, I should say. All these X's are the actual track that occurred. Since I'm running this in hindcast, I can compare the model tracks with what actually occurred, but obviously in forecast mode, you wouldn't see all these X's because you don't know where the tropical cyclone is going yet. The dark bold line is the official forecast, and that's in the Atlantic, the National Hurricane Center's official track. You can also do the same thing for intensity. The guidance is a little bit more limited. You can get a intensity number from a global model, but it's not going to be any good because the resolution isn't good. So mainly I focus on the statistical dynamical models like the statistical hurricane intensity prediction scheme, and the dynamical models like the HWRF, the COAMPS model, and the HMON are the three main groups of dynamic high resolution convection allowing dynamical models. And then you have a consensus, the IVCN, which is the solid black line, and then the official National Hurricane Center forecast given by the bold black line. So you can get a quick glance of what the models and the Hurricane Center is thinking for the intensity. Perhaps a little bit more of interest and a little bit more unique to the website is the ensemble track guidance. So there's for an ensemble, you have multiple members. So here is a graph for the ECMWF ensemble. Each of these pink lines is an individual ensemble member track. So ECMWF has 50 some plus ensemble members. The shading, what I've done is calculated a probability density based off all these ensemble members, the center passing within 150 kilometers. So this gives a percentage, is given by the color scale. So the shading you see is that percentage. And then you have some lines. You have the ECMWF ensemble mean given by the red line, the ECMWF deterministic model given by the dashed black line, and then again, the NHC forecast given by the bolder solid line. So these ensemble graphics are, I think, one of the more popular aspects of my website, and gives a kind of a quick visualization of the ensemble members. The other additional thing that I've recently added are these circles, these ovals that you see. And what these ovals represent are 90% of the members closest to the ensemble mean in 24-hour forecast increments. So 90% of the ensemble position locations at a one-day forecast lead time at 24 hours is located within this dark red circle. And then at 48 hours, this slightly lighter red circle, and so on and so on. So if you're used to these ensemble ellipses that have been popularized in some of the other ensemble graphics that you see in tropical cyclones and also mid-latitude and storm tracks, what this does is it attempts to emulate that, but it generalizes it using convex hulls in Python, basically. So the shapes you see don't have to be ellipses; they can be kind of amorphous, closed contours. So it's more of a generalization. In addition to the ECMWF, I have the GFS Canadian and UK Met ensembles as also in similar graphical form. Another thing that's really popular with my website are trend graphics. So this plot shows deterministic trends in the HWRF model. So as we go from the lighter lines to the darker lines, we go from older model runs to newer model runs. As you can see here, the initialization times increasing in time here. So what this is useful for is that if there are, say, trends, shifts in the deterministic ensemble, you can see that happening. In this case for Grace, it seems like the H-wharf was kind of bouncing around between two clusters of tracks. So I got a southerly track and a northerly track with no sort of monotonic trend in either direction, but you can kind of get a sense of those that clustering, and the verification ended up being even further south than the more southern cluster. Similarly for intensity, you can see trends in intensity. This one shows a little bit more of a monotonic trend here, again going from the older to newer model runs. Let's just focus here in this time frame, and you can see there's a trend downwards in intensity in the H-wharf runs going from older to newer model runs, and trending in the right direction, as you would hope, as the later model runs are getting closer and closer to the verifying time. So you can see it's trending in the right direction, showing more of a weak storm at this time frame. In addition to the deterministic model trends, I have ensemble trends. So very similar, showing trends in an ensemble mean track given by the blue lines going from the lighter to the darker shading. What I do for these graphics is I have a verifying time. So this shows the 72-hour verification. So this would be valid at August 18th, 2021 at 0Z, basically 3 hours after this latest, the most recent model run. So what we see here are the ensemble mean tracks up to the forecast time. So much like the determinist tracks, you just use the ensemble means to assess whether there are trends. In this case, there is a trend, a southerly trend in the ensemble mean track going forward with time, but also the ensemble ovals at the verifying forecast time. So these are the ensemble ovals at 72 hours at this time, but going from, again, older to newer model runs. I produce these for 24 hours, 48 hours, 72 hours, 96 hours, and 120 hours. And what, again, they're useful for are identifying changes in, since we're looking at ensembles now, changes in uncertainty. You can look at the ensemble ovals. The size of the ovals reflects the metric of uncertainty. So if the ovals are larger, right? The lighter shaded ovals are larger. And then as you go to the newer model runs, the oval ideally should shrink as uncertainty decreases. You don't really see that. Again, I chose an example. I was like, oh, normally you see that. But again, I chose an example where you don't really see that. Maybe a little bit here at 120 hours. There's a shrinking of the ovals, but not much. Shifts in the ensemble envelopes. You can see, in this case, the ECMWF ensemble at 120 hours shifting towards the west. So literally the whole ensemble is shifting towards the west. Again, these ovals encompass 90% of the ensemble members closest to the ensemble mean for that particular ensemble model run. And also what I find to be really interesting and useful is that depending on the orientation of these ovals, you can actually get a sense of whether the uncertainty is a long track or a cross track. For example, this oval here, this red oval, basically the purest shade of red here, has more a cross track spread relative to the track itself. More of the spread is perpendicular to the track, as you can see here. Sometimes you see the oval aligned along the track, and that would reflect more a long track spread. Really, an uncertainty then is more an uncertainty in the speed of the propagation of the storm rather than the cross-track location of the storm, which is more what this represents. So it's really interesting to see how that could evolve and how certain storms have more a long track or a cross-track spread. So really useful, at least when I'm picturing what I would find useful in making these figures, really useful for identifying these three factors in the ensembles. Verification, really important whenever we make forecasts to have verification. That's how we know how well we're doing. So first verification, figure I produced this track. This shows the 96 and 120 hour forecast position bias for all the forecasts produced for Hurricane Grace. And in this case, you can see there's a pronounced position bias, track bias, that's too far to the northeast for the models on average, except for the UK Met. I'm not sure what the UK Met office model is doing here. Definitely has it on, has less bias compared to the other models. So it definitely how it was the least bias of the models. Also, I have a similar figure for 24-hour, 48-hour, and 72-hour biases. And also the position mean absolute errors at various forecast hours. So you take all the forecasts, you calculate the error and the distance in the forecast, and you average it over the number of forecasts. Number of forecasts differs depending on the model you're looking at. So the sample size of the forecast I give by the number above the bar. This is not a homogeneous comparison, so that's important to keep in mind. But you can see that the error increases with increasing forecast lead time, as one would expect. And I have various models, I'm not plotting every model here, but the main models of interest. So you can get a sense of how the model performance is, how the official forecast from National Hurricane Center varied relative to the models. In this case, you can see, even though the sample size is small, the UK Met was certainly the best performer for Hurricane Grace on average for the storms. That will vary from storm to storm. It's not always a UK Met. ECMWF oftentimes comes out on top, but the H-Wharf, in this case, this was not a great storm for the H-Wharf, but the H-Wharf is typically a pretty good track model as well. We just did the same thing for intensity. We have the intensity bias. So positive numbers reflect that on average, the forecast was too strong. Negative numbers indicate on average, the forecast is too weak. So clearly in this case, we see a large number of the forecast models, intensity forecast models, were much too weak for Hurricane Grace, had a negative bias, except the H-Wharf. Same thing, we can do mean absolute errors for the intensity. So showing the mean absolute error in knots with increase in lead time for the various skill flow intensity models that are commonly used. Okay, sticking with the verification theme, I want to broaden it out now and look at the long-term statistics of verification. Again, verification is really important because it tells us, one, are we improving? But two, when we make changes to models, verification is really important for assessing whether those changes are useful or not. So these are graphs from the National Hurricane Center that they make publicly available. So I'll just begin with the annual average long-term track errors. And we see at all forecast lead times, the track errors have decreased and decreased quite substantially. So for instance, if we look at, let's pick 96 hours, right? In 2020, the average forecast track error was looks like about 140, 130, 140 nautical miles. That forecast, that average error is as good if we go back in time and now let's pick 48 hours. Back in the year 2000, that was an average forecast error for a 2-day forecast, a 48-hour forecast. So you can see how much skill we've gained in a pretty short amount of time, right? 2 decades, in terms of being able to forecast track more accurately. This is a huge success in tropical cyclone forecasting. So I already said that track errors have decreased significantly at all times. Why is this, right? What has led to this massive success in our ability to forecast track? So I'm just going to focus on the 48-hour forecast here in the green line. And now that green line is now the black line, and that is the official forecast. So again, these acronyms are the same ones that you saw in my figures. These are all various guidance products that the National Hurricane Center uses. And we see that there has been a decrease in errors in basically the envelope of guidance products that forecasters use. Let me just highlight one in particular, a very obscure model, not obscure at all, I should say, the GFS, which we are all familiar with. And now connecting the dots here, you can see that the GFS has really improved in its forecast error, particularly in the 90s and in the early 2000s. There's a really big drop off in error. So a lot of improvements went into the GFS to better forecast tropical cyclone track during that time frame. But in addition to improvements in global models, the emergence of specialty regional hurricane forecast models at convection allowing resolution, like the HWRF. Those are the kind of the fuchsia dots that you see here, which tend to be, clustered towards the bottom of the error range of the various models, but also development of consensus models, multi-model consensus models. And one thing that time and time again, and I know this from, making weather forecasts, not only of hurricanes, but the temperature, precipitation, wind, etc., is that when you have an unbiased, independent expert sample, oftentimes the average will beat everyone, will beat a superior forecast. And that is true here in that these symbols with the crosses and the white background are all consensus models. And those are at the bottom, the lower range of the errors of the various guidance products that the National Hurricane Center uses. In fact, the official forecast really tracks those consensus forecasts very closely. So you can see the error statistics of the consensus forecast largely mirror the error statistics of the forecasters. The forecasters know consensus products are superior, so they really, really rely on those heavily. Okay, so again, to summarize, error reduction in track errors has been a major success. Improvements in global and hurricane models resolution, improvements in physics, and improvements in data simulation. All these have contributed to the trends that you saw in the previous figure. Again, consensus techniques really have been very valuable, both multi-model and ensemble consensus techniques. And one might ask, well, how far is this going to continue into the future, right? It's a reasonable question to ask. And studies have shown that with continued model investments and improvements, track errors should continue to decrease going forward, particularly more forecasts at longer lead times. And I know it's being talked about, but perhaps we are going to see, not in the too distant future, track forecasts by the National Hurricane Center at day 6 and day 7 soon. So that's perhaps something to look forward to. Same thing with intensity. With intensity errors, we see that there's been a decrease in intensity errors. It's not been quite as pronounced as the decrease in track errors, particularly if you just focus on the left side and kind of block off what's happened after 2010 and look at this part of the graph. It's pretty flat. So for a long time, there was a lot of discussions like, oh, we're not making any headway on intensity error intensity forecast improvements, I should say. But around 2010, these curves started bending downwards, and the long-term trend now shows improvements. But a lot of that improvement is right in this time range right here. So it's almost like a step function, kind of flat here, downwards, and then flat again. So what happened here, right? What happened during this time frame to lead to this? So we can again look at the various intensity guidance products that the National Hurricane Center and other forecast centers use. This from a figure from a recent 2020 paper. Before 2006, there were really only two intensity models that forecasters used. The SHIPS model, which is a linear regression model, more or less. And then the GFDL model, which is a numerical, a dynamical model that's been around for quite a long time. And the errors associated with those were relatively flat, right? So in terms of making intensity forecasts, this is what the National Hurricane was relying on. That's why there wasn't really much improvement, right? There's very, very little intensity guidance, and intensity guidance wasn't really improving during that time. And in fact, you might look at the bottom acronyms here. This represents the most skillful model in that particular year. So the statistical dynamical guidance, the SHIPS model, again, just a multilinear, multivariate linear regression model, was beating our dynamical guidance pretty badly too. So that was our best guidance, but something happened in 2006. You see a bunch of lines emerging. That was when there was an increase in dynamical guidance. You see the Elgin model, which is kind of a hybrid parametric but time-dependent model. And then the HMON and COAMPS and all those other models began to emerge in this time frame. And then the second black line represents when the hurricane forecast improvement project started. There's a big initiative, big injection of money into improving dynamical guidance. And this was a game changer. From this point forward, and particularly in the most recent years, the HWRF model is vastly the most superior intensity guidance model we have. But there was improvements basically in all these intensity guidance products in this time frame. So a lot of science, a lot of research to operations efforts, really a tremendous success in bridging the science to operations was done over a pretty short time frame to pull down these errors significantly. Okay, so the successes, develop improvements in dynamical hurricane models at convection allowing resolution to HWRF. Certainly I remember looking at the HWRF, I'm like, wow, this is really a leaps and bounds in the early, about a decade ago of improvements. And HFIP was a big part of that. But also the track forecasts, right, have improved. So stands to reason because the track forecast improved and the forecast of large scale environment around tropical cyclones will result in better intensity forecast because you're resolving the factors that affect intensity. Track, for instance, if a hurricane makes landfall, has a huge effect on intensity. So all those improvements in track forecasts have had the consequence of also improving our intensity forecast. But there are challenges that remain. The vortex initialization of forecast models is a really difficult problem. Seems like an obvious thing. Just put a hurricane in a model, right? It's just do it, right? But assimilating tropical cyclone observations when they're available, right? And they're not available in every basin. It's a really difficult problem. There's large uncertainty in physics in hurricane environments. Again, just attended the AMS conference on hurricanes and tropical meteorology. Large number of talks focusing on better estimates of parameters, better representation of physics in hurricane environments, particularly in the boundary layer and the air-sea interface. So really not friendly parts of the hurricane to observe. So there's huge error bars in a lot of the parameters and physics associated with hurricane environments. And environments that cause inherently large uncertainty. For example, one environment that I'm really interested in is moderate shear, where there's shear between kind of the lower to middle troposphere and upper troposphere around the tropical cyclone is in a range of about 10 to 20 knots. This can cause weakening to rapid intensification. We observe a range of behaviors, and environments like this where there's a lot of sensitivity pose problems for numerical models to predict intensity well. And also there's predictability limits. You can have a perfect model, right? This is a very nonlinear system, convective, moist convection, small errors grow really fast, right? So there's going to be a saturation in what we can do to predict hurricanes, even if we have a perfect model. So this is just a difficult problem all around. Improving forecasts of rapid intensification is an area of particular focus. So rapid intensification occurs when a tropical cyclone intensifies by at least 30 knots in 24 hours. So if we look at the error statistics, this figure from Fisher et al. 2019 for periods where tropical cyclones undergo rapid intensification versus periods where they don't, the mean absolute errors, I should say. Rapid intensification storms are way higher, right, in terms of this red line here. Models and forecasters really struggle with the prediction of rapid intensification. So this represents another challenge where there's been a lot of focus on over the last decade or so, and remains a challenge going forward. So looking forward, and this is my last slide, there's reason to be hopeful. Continued model and data simulation improvements, along with the emergence of convection allowing hurricane ensembles. It's something I'm really excited about. Really have the potential to improve the number of guidance products we have, and to be able to quantify uncertainty, things like that, will really be something that I think is merging on in the next few years. Machine learning and artificial intelligence. These approaches, especially when combined with the dynamical approaches, I think have a lot of potential here. There's a lot of publications coming out about machine learning and AI techniques, both in terms of track and intensity forecasts. And as those mature and they get pushed into the operational realm, I think will be promise there. I know there's already a lot there on severe weather front, and I think hurricanes will be an area where this house also has contributions. And the new observational platforms, things like unmanned aircraft systems. There's a sail drone that was deployed last year in an experimental mode and actually got into Hurricane Sam and was able, when Hurricane Sam was a Category 4 storm. So this is really exciting because we can, using these systems, we can gather critical data in really important regions like the boundary layer, where you're not going to be able to fly a manned aircraft through. So I think this poses a lot of potential as well. So I think that's it. And I'll leave it there and be happy to take any questions.
Well, first of all, let me just say that this is amazing. I think you packed basically like a semester's worth of material here in a 30-minute presentation. And I know I'm biased, but let me just say that I've been an operational forecaster for most of my career, but I think the work that like you do in general, the tropical community in terms of probabilistic forecasts, moving forward probabilistic forecasts, objective forecasts, I think is just, it's right there at the cutting edge, and there's so much to learn from it. And in particular, some of those new tools you showed with the ellipses and such, that was really some great stuff. But unfortunately, it looks like we're just about out of time here, so I don't think we're gonna have time for too much more. Again, I hope everyone else found this discussion as interesting as I did. And Professor Tang, I hope we can have you back again in the future to talk about things. Heck, we didn't talk, climate change, seasonal outlooks, other type of impacts and such. So I hope we can have you back again in the future. And finally, we will, for folks who maybe didn't see the whole thing, we're recording this and we will post it on our YouTube channel. So we hope you can watch it there. So again, Brian, Professor Tang, thank you so much and hope to see you again soon.
Thank you.